Okay, so we're going to start off with L'Hopital's rule. So we're going to state it first. So assume that we've got two functions. They're differentiable in an open interval containing a. And assume also that the two functions are equal to 0 at that point a. So then what L'Hopital's rule says is that the limit as x approaches a of f of x over g of x is equal to the derivative f prime over g prime. And so basically remember that here this is an indeterminate form, and so basically what this is saying is that if you get a indeterminate form of the type 0 over 0, that you can just get the derivative of the numerator and the derivative of the denominator and find that limit, and many times this will then give us a conclusion. Now also I want to point out that this also holds for when the limit on top and the bottom is infinity over infinity. So let's put that down right here. Okay, so if you get infinity over infinity on top and on bottom, you can use this same rule. And so there you go, it's infinity. Whoop, 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 whoop. Okay. Okay, getting out of hand here. Okay, anyways, sorry. Alright, so let's prove it for the first case, just 0 over 0. And it's not too difficult to see. Let's start off with the definition. Now, let's do a little, let me write down here something to remember so that we, this makes a little bit more sense. The derivative at a, I'm going to use this definition. So this is equal to the limit as x approaches a of f of x minus f at a over x minus a. So remember, this is the alternative definition instead of x plus h. Okay, so let's start off with this guy right here. Let me change the color. That's a little dark for my eyes. Okay, so we've got the limit as x approaches a of f of x over g of x. And so I'm going to say that since f of a and g of a are equal to 0, well, then this is the same as the limit as x approaches a of f of x minus f of a over g of x minus g of a. So all I did was these guys are just 0 by the assumptions right here, so just subtracted them and then just divide the top and the bottom by x minus a, and then we basically get the result. So check this out. Limit as x approaches a of f of x minus f of a. Let me scroll down here. It's not very easy to draw on the tablet. Okay, g of x minus g of a, and then so what I'm doing is I'm going to divide the numerator by x minus a and the denominator by x minus a. And so then what I've got is basically this right here, that's f prime, and this right here is g prime. And that's it. Okay, so let me show you an example of how this works. And then you guys can do the examples on the handout, video handout. So let's say, for example, you've got, and then don't forget also that this works for infinity over infinity. So let's do, remember this one that gave us a lot of trouble. the limit as x approaches 0 of sine x over x. So the first thing you want to do is just like we usually do. You plug it in. So if I plug it in, I'm going to get 0 over 0, right? You plug in 0 here and 0 here. You get 0 over 0, which is indeterminate. And because it's 0 over 0, if it's 0 over 0 or infinity over infinity, you can use L'Hopital's rule. So what L'Hopital's rule says is this is equal to the limit as x approaches 0 of get the derivative of the top and the derivative of the bottom. So very important, do not use the quotient rule. We're just getting the derivative of the top and the derivative of the bottom. So I get the derivative of the top, which is cosine, and then the derivative of the bottom, which is just 1, and then you just try again. So you again plug in the same value, 0, but this time notice cosine of 0 is just equal to 1, and that's it. You're done. Okay. So that's L'Hopital's rule. So very handy for trig functions, exponential functions. There are other functions that aren't, you can't do them without using L'Hopital's rule, and you can see those on the the video handout, and we'll go over them in class. Another topic that we want to talk about that's related is the dominance of functions. So, for example, let's look at x cubed and e to the x. Here, the purple right here is x to the third, and the blue is e to the x. So notice how here there's an intersection point here, and x to the third is larger than e to the x, but there comes a point when e to the x dominates the situation and is always going to be bigger. So that's what we mean by dominance. Dominance is who gets, as x goes to infinity, what function is dominating the other, which one is gets larger faster. So we say that f of x dominates g of x if either one of the two following holds. If either the limit as x goes to infinity of f of x over g of x is equal to infinity, so that means that the top is getting fast bigger than the bottom is, or the limit as x approaches infinity of g of x over f of x is equal to 0. And so it's easily seen why, using L'Hopital's rule, you can easily see why e to the x dominates x raised to any power for any n. And so we're not going to go through the entire proof, but let me just show you, for example, if I do the limit as x approaches infinity of e to the x over x to any power. Let's just pick, just randomly, let's just say to the fourth. But this works exactly the same way with 5, 6, 7, 100, 1,000. Is that notice that you plug it in, and so you would get infinity over infinity, right? So infinity on top, infinity on bottom, which tells you, okay, you can use the L'Hopital's rule. So you get the derivative, just like we did in the example above, and then you get on the top, the derivative of e to the x is just e to the x. The derivative of x to the fourth is 4x to the third. Okay, so then you get infinity over infinity again. And so notice that the top is always going to be e to the x. The bottom is going to, at the next step, you're going to get 12x squared. Then the next time you do it, top is going to be e to the x again. The bottom is going to be 24x. And then next time, top is going to still be e to the x, and the bottom is going to be 24. And so then this guy is going definitely to infinity. So e to the x is going to dominate this one always. And you can do this for any function. Alright, so that's it. So work out the video examples.